Hello, good morning, guys. Welcome back again to the physics sessions with me, Fazil, your host tutor. So, now, today we will be learning about the possible ray diagrams that can be made using a lens. The two type of lenses, the two type of spherical lenses, which you were studying all these days in your previous sessions. I would like to introduce the ray diagrams, basic ray diagrams of these lenses. So the basic two lenses that you have learnt about in your past classes were the 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 concave lens, and you had this convex lens. So you had concave lens, you had this convex lens. So today we will be studying the ray diagrams made by them. So I will be teaching you the fundamental ray diagrams of these two lenses. Along with that, we will be learning about two more things. One topic would be about the the glass lab refraction. Actually, the heading of your subject looks a bit different because in textbook it is given refraction through a glass lab. So anyways, both thing mean the same. Okay, so we will be dealing with glass lab refraction. In addition to that, there will be a study quantitative study of lenses. So what is this quantitative studies? In a quantitative study, you are going to be learning about some numbers, maybe equations. So what is the equation, or what is the quantitative uh, thing that you are going to study here? It is obviously the lens formula. The lens formula. Just like in the case of a mirror, you will be learning about a formula in lens. So let us go into each detail, each in good detail right now. So the ray diagrams, the possible ray diagrams for convex lens. Let me teach you about convex lens first, and then I will go in detail about the concave lens. So convex lens, ray diagram for convex lens. So how do you study the ray diagram for a convex lens? Let me show you. As stated earlier in one of my lectures, to draw a ray diagram, you may basically need three things, a few things, not just three things, but a few things. The main thing is that you need to represent the lens. So there it is. You have your convex lens, since you know the refracting interfaces, this interface and this interface must be bulged outward. Okay, what else do you need? You might need a, say, principal, maybe you may need a, a principal axis. So you need a principal axis, very good, and the principal axis is placed such that half of the lens is on top of the axis and rest half remains underneath. So this is symmetry. You have a symmetry. Okay, so half is here, half is here. So this must be placed at exactly the center of the lens, and this point is called the pole. The center, the geometric center of the lens is called the pole, through where the principal axis passes. Now what else? Now next you need to understand the conventions. So what are the conventions? Conventions are exactly similar to what you have learned in your mirror study. So what were the conventions? So you have pole. Let me just move it a bit, align with the, keep it a bit aligned with the pole. Pole is your origin. Now you have two axes. You have this vertical y axis, you have the horizontal x axis. So this is the y axis and this is your x axis. As you know, as you have studied from your coordinate geometry in mathematics, uh, this is positive x, this is positive x, this is negative x, negative x. So that is negative and this is positive side. And as you move up, it is positive y, and as you go down, it is negative y. So these are the basic conventions you need to keep in mind. So how do you make use of these conventions? See, you are going to place the object, the source of light, object or the source of light, maybe, yeah, always you place the object on the negative side because it is more convenient uh, to draw it that way. It is not that minus has any preference, but we keep it on the negative side because it is very convenient for us to draw sequentially, because we write from left to right. So that is why we keep objects on the left. That's all. There is nothing more to it than that. So you have this object. So this is your object. Now one thing you need to know is the object is placed on the left side. Now where do you keep the object? The reference of the object or the position of the object is measured with respect to the pole. So pole is your reference because it is the origin. So you measure the distance of the object from the pole. So this is the position of the object and we represent it using the letter u. Now the value of u, how do you select the value of u? See, you might have learned, no, you should have learned it because I have taught you earlier. You should have learned that from your previous classes that a lens has two centers of curvature, one on this side and I call it C1, and one on the other side and I call it C2. And light rays traveling parallel to each other, one another, and parallel to the principal axis. Listen to me carefully. Light rays traveling parallel to each other and parallel to the principal axis converge on a point on the principal axis and we call it the focus. And on this side I call it F2, on this side I call it F1. See, F1 and F2 are actually the focuses of this lens, and there is a predetermined relationship between the distance, I mean the distance of the focus from the pole to the distance of the center of curvature from the pole. What was the distance of the focus from the pole called? It was called the focus. So focal length. So you have this focal length over here and exactly same distance to this focus on the other side. So this is the focal length. What is focal length? Focal length is the distance of the focus from the pole. Now what is the distance of the center of curvature from the pole? The distance of the center of curvature from the pole, I could call it the radius of curvature. So you have this distance, the distance from center of curvature to the pole is known as the radius of curvature. Exactly same on the other side, r from here till here. See, why have I drawn it that way? Because it coincides with the center of curvature. So r is the center of r is the radius of curvature and f is the focal length. So there is a relation connecting r and f, and you might have guessed it exactly. The radius of curvature is equal to 2 times the focal length. So this is a very good relation, a very useful one in fact. So just remember it. Okay. So now we have determined the distances of the object, of the focus, and the centers of curvature. All right. So any distance you measure to this side will be negative, and any distances that you measure to that side will be positive. So remember this too. When you use the formula or the lens formula, you will need this convention. Okay. So let us get into the details of ray diagram. So I have removed all the extra points, but just keep in mind that they exist there. Okay. So they are all present there. Now what is now left is to draw the ray diagram for a given object. Now we draw the ray diagram for various for various values of u. What was u? U was the object position or the object distance. I would prefer calling it object position because there is a typical reason for why it is called object position instead of object distance. But in your exams, this will be mentioned as object distance. So don't get confused. So I am going to write that too. This can also be referred to as object distance. So take that too. Okay. All right. So how do I see? This is a qualitative study. Right now I am doing is a qualitative study where you are not going to use any numbers to compare things. All you are going to say is whether it is far away, whether it is close, whether it is near to something. So there will be no numbers. Qualitative study is always without numbers, and quantitative study is always with numbers. So now I am going to do is qualitative study. So how do you do the qualitative study? You make the ray diagram. So for that, let me mark a few things. See, throughout the ray diagram studies, I will be keeping the object on the negative x-axis. So any distance measured to the negative axis will be negative. So object, before I go into the object, let me mark the center of curvature. So this side the center of curvature was C1, and let me mark the focus. I'll call it F1. All right, and on the other side also we have is the F2, and we had the center of curvature 2. All right, first ray diagram. Let me draw a box over here. Representing two things, where where the u is u. So where the object is going to be placed. So we need to know where the u is, and one more thing, where the image of this object will be obtained. So v, what is v? V is the object distance. Sorry, the image distance or the position of the image. V is the position of the image, or it is also known as the distance of the object, the distance of the image from the pole. So everything is measured with respect to the pole. So V is the distance of the image from the pole. Okay. So V, you have given the V. Now what else do you require? Now you need to know the nature of the image. So nature of the image. Nature of the image. So nature of the image. See, in just similar to the case of mirrors, nature of the image consists of three main parts. First, you need to compare the size. You need to know the size. So let me just re-bracket one more thing. size, and then we have the type of image, whether it is virtual or real. Okay, so type refers to that. And one more thing, whether the image obtained is the orientation of the image. So I will call it the orientation. I guess orientation, you can see that. So orientation refers to whether the object is inverted or erect. Okay, now where do I want to keep the object first? Let me just show you this table clearly. First, the object, I'm going to place the object. Where do you want to place the object? Yeah, let me place the object at infinity. Very far away. Let us go and see where will I obtain the image at. Okay, you might have already guessed it. Any ray from an infinitely far away object will always be how will it be? It will be parallel rays. So it will be parallel rays. So any ray coming from an object placed at infinity will have parallel rays. See, only number of rays you require to describe the image are 2 rays out of 3 choices, if you remember. So for an object kept at infinity, there are only the rays will be always parallel to each other. So you have 2 rays which are moving parallel to one another. Where would they meet? Exactly, as you guessed, they will pass each other, they will intersect each other at the focus. So your image is at the focus. So whatever the size of the object be, because it can be, it is obviously of a finite size, it will have a size, but as its image is formed on the focus, the size of the image has become so diminished. So there is your image. Now where is the image is over here. Okay, the image is over here, and the distance of the image from the object is v, and you already know f2 is at a distance of f. So your object is formed at the focus, and the distance of the object v is equal to f. So there it is, there your image is. The size of the image is extremely tiny. You have a very extremely tiny image, so size is so low, and as you can see, it is formed by 2 rays intersecting. So the real rays are intersecting, and you can form this image on a screen. This image is formed on the right side of the mirror, sorry, the lens. Object was on the left side and the image is formed on the right side. So this image, which can be casted on a screen and has been formed by the intersection of real rays, will give you real type of object. So let me get into the details over here. So where was the object formed? The image formed. The image was formed at the focus. And let us go and describe size. What do you want to say about the size? It is extremely small. So I will call it diminished. And what is the type of image? The type of image is real. So we have a real image. And what was the orientation? See, the orientation of this object at the focus is mostly taken to be inverted. So you have inverted image. So you have this case for the first U. Let us go on to the second U. For the convex lens. Okay, so now we are going to keep the object beyond C1. I'm not going to keep it at infinity, but I'm going to bring the object very close to the lens. So where is this object? Let me give you an idea of, if you are holding the lens inside your classroom, okay, if you are holding the lens inside your classroom, then this object could be somebody walking on the veranda, possibly, because if your lens is too small and thin, or maybe thin, then this object could be somebody walking on the veranda, maybe a teacher going from one class to another. So you are holding this lens, or it could be a coconut tree outside. This object could be a coconut tree outside in the courtyard. It could be anything. It's not at infinity, it's not at very far away, it's not like stars, moon. It's like a tree very close to you or your classroom or where the lens is. Okay, so that's what you would get. So your object AB is here, so don't mind the rest of the diagram. Your object AB is here, and you have see, from the on the object AB you have several points. Now just consider the point A, so tip of the object. From that point you need two rays to construct the image. See, for this purpose, to construct the image, I have used two rays. One ray is this one, which is moving parallel to the principal axis, because it is the most convenient ray to be used, because it would result in a refracted ray which goes through the focus. See, as you can see, the ray running parallel to the principal axis actually goes through the focus on the other side. The second ray, the convenient one, would be, out of the three choices, I would be using a ray which goes through the pole. Okay, so I'm going to use a ray which goes through the pole. What happens to a ray which goes through the pole? It goes undeviated and it goes straight. So straight. So on the other side, look at the point where these two rays intersect, and it's over here. So this is where the image of the point A will be formed, because these rays are coming from the point A. So this will be the image of A, and I'm going to call it A prime. A prime is the image of the point A. Similar to that, we can construct the entire image, and we will end up in such a diagram where A prime is the image of A and B prime is the image of B, and you get is an image. So where is the image located? Now the image is located between the center of curvature and focus on the other side. So the image is now between C2 and F2. Okay, your image is A prime B. Let us go ahead and compare the sizes. If I draw the object and the image side by side, you can see the object is erect, but the image is inverted. The object is large, but the image is small. So also, as you can see, these are real rays. These rays are real. You can block these rays. So these rays are real, and they can be casted on a screen. So this image A prime, which can be casted on a screen and is formed using real rays, is called a not a virtual but a real image. So you have what you have here is a real image. So you have a diminished size image, you have an inverted image, and you have a real image. So let me go ahead and tabulate it. So you had placed the object beyond C, and now the image formed is between C and F on the other side. And what do you have to say about the nature? Small, real, and inverted. The image is small and it is real and it is inverted. See, okay, so let me just go on ahead to the next ray diagram. So let's go into the next diagram. Where do you want to place the object? Now I am going to place the object not beyond C1 but on C1 at the center of curvature. How would you form the image of? Let me mark it A on top and B on the bottom, so you can recognize the image as AB. Sorry, the object as AB. You have several points on AB. Let me choose the point A. Now again you draw the ray diagram. You can use two rays from this coming from this point. The first ray that I'm going to use is this ray, the ray running parallel to the principal axis. Now what about the second ray? What happens to this ray? It's very easy. It goes to the principal focus on the other side. So it goes to the principal focus on the other side. So it is as easy as that. Okay, it is as easy as that. Okay, okay. All right. Oh, I'm so sorry. My drawing skills are very poor, especially when I'm handling it on a electronic device. So let me correct the focus. So the focus is here. All right. So what happens to the which ray would you consider as the second ray? Second ray, for the second ray, I would again consider maybe a ray which is going through the pole. So it's coming from A, it's going to the pole. Oops, yeah, going to the pole, and there it goes. So there, where are you? Oh my god, yeah. So that is how your, where is it? See, I cannot control it. Okay, there is your second ray. First ray went, and first ray went through this part, second ray went to that part. So the pole ray going to the pole goes undeviated. Now where is the image? Now what about the image? See, this is the image of point A, so I will call it A prime, and this would be the image of point B, so I will call it B prime, and you get is an inverted image, Drawing these A prime, B prime side by side, let me show you how do they look. So if this was your AB, this was your AB, and this must be your A prime, B prime, A prime, B prime. So comparing the sizes, what could you say about the sizes? They are of both same sizes, same sizes. Okay, same size. What about the orientation? Obviously the image is inverted. And what about the nature? Since for a lens, see, for a convex lens, if the image is formed on the right side or the positive side, then it will always be called a real, it will always be a real image, because for a convex case only. Okay, when you come to concave lens, this won't be the case. All right. So for lenses, real images are always formed on the opposite side of the object. So images formed on the opposite side of where the object is will be will always be real images for lenses. Okay. So let me just tabulate this again. So where is the object? So, object place? The object was placed at C1, and the image was formed at C2. Wow, that's good. So it's one of a good example for ray diagram. So let me extend these lines. Whoops, and again, and hell. Yeah. So where was the object? The object U was at C. So you have at C, and where was the image form? Again at C. See, it is C1 in specific, and this must be C2. So you understand where they are. And what about the sizes? The sizes of the object, I mean nature of the object of the image was, the size of the image was, it is same size as that of the object. What is the type? Again, you have a real image, and of course you have a inverted image. You have an inverted image. Okay. So this is what happens. Now again, moving on to next ray diagram. Okay. Now I'm going to keep the object at between C1 and F1. So I'm going to keep the object here. Why am I making the object smaller and smaller? See, the purpose of making the object smaller and smaller is to encompass it between the aperture of the lens. So whenever you keep an object, that object must have a size under the limits of its aperture. So what is aperture? Aperture is actually the diameter of the lens. Okay. So now the object is placed between C1 and F1. What happens to the image of this object? Let us go trace it. Again, I can call the top point A and the bottom point B. So what happens to the point A? Let me see what happens to the point A. So there your point A was. Now drawing a ray from A, I can use two rays. One ray would be the ray parallel, and obviously you know what happens to it. It goes through the focus on the other side. So let me draw the direction. Okay. Second ray that I'm going to use would be, again conveniently, I would be using the ray coming from here, from A, and what happens to the ray? It goes through the pole. Oops, it's extending beyond the screen limits. So possibly I should be moving the screen a little bit onto the side. Okay. So as you can see, the rays move like this. This is the location, this is the point where they intersect, they meet, and that point will be the image of A, and I will call it A prime. Similar to that, you will get an image of B over here, and I will call that B prime, and if you extend it, you will know the image of the whole object. Wow, that's good. Now you are coming to somewhere. You have AB and its image is A prime B prime, and let me draw it side by side to show you how do they compare. Where is the object placed? It is placed between C1. It is placed between C1 and F1. Where is the object? It is formed beyond C2, beyond the center of curvature on the other side. See, as the object comes closer and closer to the lens, the image starts receding away from the lens. So that is the trend that you are seeing now. Okay, just don't generalize it, but you seem to learn that pattern here. Okay, comparing the sizes of the object side by side, object and the image. The object was a small one. You had the object AB. Now the image was A prime B prime, A prime B prime. Again, what are the three distinctive feature of the image as compared to the object? As you can see, the size enlarged. See, the image is now enlarged. Orientation inverted. What type of image is it? See, it's formed on the right side and the object is on the left side, so it also the rays intersect to form in the real world. So it is, so you see, this these rays actually intersect in real world. They are actually intersecting in real world. The upper ray and the lower ray intersect in real world, and also they can be casted on a screen. So they are real images. So these are the three nature of images. So let me just tabulate that too over here. Your object was between C and F, C1 and F1. And where is the object? Object is the image is formed beyond C2. Nature, size was enlarged, the image was enlarged, real, of course, real, and then inverted. So you have this. What about the what else do we have here? Nothing else. Now we are going to move ahead and place the object a bit more at a bit more different locations, a few more different locations. But see, I will just roughly tell you about what happens to an object placed at focus. See, when an object is placed at focus, all of it is not on the principal focus. Okay, only the part of the entire object which intersects with the principal axis. So this is the lens and this is the principal, this one is the principal axis, and if this is the object, not all the points of the object are on the focus, only the point that intersects with the principal axis is on the focus. And this point, I'm going to draw the image of this point only. So the image of that point will be, see, which ray would you use? I would be using, since it's coming from focus, see, I can use a ray parallel, but okay, I'm going to use a ray parallel, moving parallel to it. Okay, so that is your first ray, ray 1 coming and going, passing through the lens. What about second ray? Okay, again I can use a ray which is moving through the pole of the mirror, pole of the lens. So that ray I'm going to represent using maybe red, so that you can see it distinctively. So it's also coinciding with the previous ray, right? It's running over the first ray. So what will happen to these two rays? Where will they meet? Will they meet here, here, here? Where? Actually they seem to be meeting everywhere, but no, they are not at all intersecting. These two rays are running parallel to one another. And where do parallel rays or lines meet? Where do they meet? They meet at infinity. They never meet. That is what infinity physically means. They never meet. So again, size of the object is finite size, but still you are only assuming a point size object, so it is a very small object, but the image will be a large one. Where was it? It was at f1, at the focus. Where was the image? At infinity. And you have size of the image is actually large or enlarged. What about the nature? It's, if you were present at infinity, you could have casted a real image, but I don't know, it's partly between real and virtual. I can only say that it's not real, it's not virtual. There is no image formed, in fact, so you don't have to even mention about the nature. See, so I'm not going to write enlarge, or I'm not going to mention whether it is real or virtual, and there is no need to mention whether it is inverted or upright. Okay, so objects kept at focus seem to form no image. That is what this infinity means. Okay, so infinity has some meaningfulness in this particular case, not every case, but in this particular case at least infinity has some meaning. See, if you might have heard of black holes, black hole is full of infinities, and that is where most of the physics goes meaningless. But in this case, that is not the case. It's just, it means the image is not formed. So where else could you keep the object? Where else? Let us go ahead and look at the ray diagram. Since I have the last place that I have kept the object was at F. Now I can go between F1 and P, the focus and P. So let me tabulate it first. So now the object is kept between, so let me write between two so that you don't get confused. Between f specifically f1 and p, there is only one p. So where is the image going to be formed? This is a bit tricky ray diagram, so be with me. Okay, I will teach you how this works. Let me make a large aperture lens because I'm going to keep the object very close to the lens. So you have is here your principal axis. Let me make a very tiny weeny image. First of all, let me mark the center of curvature. Center of curvature, here is your C1, here is your F1, and here is your P, and here is your F2, and here is your C2. See, C2, F2, F1, etc. should be placed symmetrically about the pole because you are studying about a biconcave lens, biconvex lens, and it's symmetric, yeah, for this particular case. Where is the object? So we keep the object here. Okay, listen carefully. Okay, now we will go ahead with two rays. Again, I can write this upper point will be A and the bottom point will be B. Now let me draw the rays. Draw the rays. Excuse me for the slips. Okay, let me draw the ray. You have a parallel ray. Okay, no problem. Where would it go through? It would go through the focus. Let me use not green color, but instead I can use purple color so that ray would be distinct. Okay, that ray went happily ever after. What about the next ray? Okay, I will use a ray that goes through the principal, the pole. Okay, I'm going to use which is moving to the pole. Oops, I think I made a mistake. So yeah, now it seems to be almost good. Yeah, so yeah, there it is. Do you see anything in peculiar about those two rays? Don't you see they are not running parallel? Of course they are not running parallel, and of course they are not converging. They seem to be diverging away from one another. One is going to that side, the other one is going to this side. And let me assure you of something, never will two rays diverging away converge. They will never intersect. Oh my god. So there is no intersection, or there is no point where these two rays will meet in real life. Okay, in the real life they will never meet each other. Oh, so that is an issue. What are you going to do now? By the way, you are going to, you will have to keep your eyes on the other side. So there is no good reason to place a screen on the other side because there will be no images obtained on the other side because there is no intersection. Of course, if two rays would have intersected, then we would have an image. But what about now? In this case, but you can see on the other side the ray 1 appears to be coming from somewhere from this direction. So it appears, see, this is the apparent region from where the ray appears to be coming. So this is not a real ray, it is only an extended version of the ray. So the ray appears to be coming from this side. What about this ray? The second ray, this ray. This ray also appears to be coming from, I don't know, from somewhere beyond. And both ray then appear to be coming from a common point. Oh, that's good, that's good. So this common point will now be the image as seen. Okay, this will be the image of A. So I call it A prime, and that will be the image, apparent image of point A. Extending it downwards, we will get B prime, the image of B. Oh, that's so nice. You're never going to get an image in the real life, but you have to extend it into the virtual world. You're extending the ray into the virtual world. So that is where the image appears to be. It only appears to be, it does not exist, it only appears to be there. So in real life the image does not exist because these two rays never converge, they always keep on diverging. So let me just compare the sizes and the nature. Here you had the image A prime B prime, and here you had the object A B. It's very clear that the image is enlarged. The image is enlarged. What about the orientation? It's, of course, it's erect. It's erect. And the type of the image, is it in the real world? No, it's just an apparent image. It only appears to be there, which means it's not a real image, but it's instead called a virtual image. So it's virtual. So tabulating when the object is between F1, the focus, and the pole, what is the location? Location is, I cannot say where exactly it is formed, but I would call it on the same side, on the same side as the object. See, object and image are now on the same side. Ooh, that itself is a good omen that the image formed is a virtual one. What about the size of the object? Size was enlarged. See, it is a good thing because it is being used to make microscope. So yeah, which you will learn later, possibly in your 12th standard. So you have a enlarged image. What is the type? Is it real? No, it's not at all real. It's virtual. It's only an apparent image. So it's a virtual image. So see, virtual image is apparent image, in fact. Okay, so it does not forms in real life. It forms in a virtual world. So what is the orientation? Of course, it's erect. See, as you can see from the pattern, real and inverted come in pair, whereas virtual and erect come in pair. There's only one case for virtual and erect is in our lens. So this is your table where all the entire nature and all those things are given. So if you want, you can take a screenshot, otherwise you can just go through the video several number of times. So that's it. What about now? We will be learning about the ray diagram of a concave lens. Was the video posted? No, yeah, concave lens. So concave lens has not a complicated ray diagram. In fact, there is only one single ray diagram for a concave lens, because that is a good representative of every other ray diagram for the concave lens, because wherever you keep the object, you are always going to get the image, the nature of the image similar to the previous. So whether you keep it is actually like u, whether the u is far away at infinity or it is beyond f or c or wherever, the nature of the image is always going to look the same. So for that reason, for that particular reason, we only draw one ray diagram, because that represents for every variation of u. Okay, for every variation of u, you're going to get the same type of drawing, same type of image, I mean ray diagram. So just let me get into that. How does it look? So there is your it's not very good, but still, yeah, there is your concave lens and there is your principal axis. So ray diagram of a concave lens, see, I'm not going to put any c's or any f's, because wherever the object is, okay, I'm going to, it can be anywhere on the negative x-axis. So nothing much to it. Okay, so it can be placed anywhere between p and infinity. Okay, here your p is over here, you have your p here and you have infinity. So the object is kept between infinity and p, that's all. Now about the ray diagram, what about the ray diagram? Similar to the case of I mean, out of the three choices, I'm going to use the parallel ray one. So the parallel ray, I have the parallel ray. Let me draw a small arrow indicating the movement. What happens to this ray? This ray diverges exactly. Since this is a diverging lens, you have a divergent ray. Okay, you had a divergent ray. Now, yeah, it's supposed to be not diverging that way, but let me just redraw it correctly. So you have your divergent ray like that. How does it diverge? It diverges as if it appears to be coming from the focus. Now what about the second ray? I'm going to draw the second ray. Which I'm going to draw this time will be passing through the pole. So there is your second ray. It's quite obvious that these two rays will never converge in the real life. In the real world, they are never going to converge. See, the first ray appears to be coming from some point. The focus appears to be coming from the focus, and this ray, which is in fact crossing the pole, appears exactly to be coming from that same direction. When you look at this ray, it's coming from that direction because it has come undeviated, right? So as you extend it beyond, you will see it comes from. So where is your image now? These apparent rays, when they intersect at some point, and there is where your image is formed. So there is your image. If this was A, this would be A prime, and if this was B, this would be your B prime. So let me draw it with a different color so that you can distinctively see that. Yeah, there is your A prime, B prime. See, in every situation, whether the object is here, if it is placed here or anywhere between F and P, this is what is going to happen. What is the common trend that's going to happen or repeat is you have the image, you have the object A, B, and the image will always be a tiny weeny one like this, a prime b prime, it will always be erect. So the nature, comparing the image to the object, you have a diminished image, you have a diminished image, you have a, what is the nature? It's not real, it's not in the real world, so it's a virtual image. Obviously it's a virtual image. What about the orientation? It's erect. So for every case, see, I might have made a mistake in previous spellings of erect. Erect is no, it is erect is actually ERECT, I guess. Yeah, it's one of them. Okay, just learn it. It's going to be one of them. No, it's not going to be any of them. It should be one of them, and that spelling correct is not this one. It's the correct spelling is ERECT. Okay, the correct spelling is ERECT. So don't mistake it. So this is what happens to in the case of a concave lens. So that's it. So you have only, when you, if you want to tabulate things, then you have only this a few things to say, and the few things would include, where is the u? U is anywhere between infinity and p. So, and v, where is v? The v will always be formed. See, the position of the object is always formed, I mean where the image is always formed between, that is a bit different aspect about this concave lens, that the image is always formed between f1 and p. F1 and p. Whether the object is placed between infinity or between anywhere between infinity and p, the image is always formed between f1 and p, the focus and the pole. So talking about the nature, what are the three distinct features? Size is diminished, tiny, diminished. What about the type? It's obviously virtual. And what about the orientation? It's erect. So you have virtual, you have erect, and you have a diminished object, and which is always formed between f1 and p. So these are the things about your your ray diagrams of the two lenses, the concave lens and the convex lens. So now let me move on to the mirror formula. Sorry, not the mirror formula, but the lens formula. So we have the lens formula. So there is no derivation which you study in your 10th standard about the lens formula, but I am going to straight up give you what it is. Again, lens formula is a relation between object distance, image distance, and focal length of the lens. So u, v and f. So it's a relation. Lens formula is a relation connecting u, v and f. And the formula is this: 1 by v minus 1 by u equals 1 over f. So there you go. There is your relation. Let me put it inside a box so that it appears to be important. What is v? It's the image distance. So let me write that down too. V, explaining the terms, it's very important because yeah, that must be done, because for anybody looking into the equation should understand what each term means. V is the image position or image distance. I will call it image distance in this case. Image distance. What about u? U is the object distance, and f is the focal length, of the lens. So this mirror, this lens formula, this is the lens formula. You have the lens formula. This lens formula is valid for both concave and convex lenses. So this is valid for concave and convex lenses. That's a spelling mistake. It should be lenses. Okay. So you have your lens formula is valid for both type of lenses. So that's your lens formula. So that's what's all about lenses. So the lens formula will be used to study all this image formation quantitatively, because from this table you do not know, from this table, as you can see, where exactly has the object been placed is unknown, and where exactly is the object of the image obtained is still unknown. And also how large, how small the image is with respect to the object is also unknown. Yeah, there is one more formula that I forgot to teach you, and that formula is about the magnification. It's about the magnification of lenses. Just similar to the mirrors, the magnification is defined here, but it's a bit different as compared to the magnification of mirrors. Magnification of lenses, M, is defined as the ratio of the height of the image to the height of the object. So there you have one equation for the magnification, and this is the definition. The definition of magnification is height of the image, the ratio of the height of the image to the height of the object. See, height is just a one-dimensional scenario. If it comes to a three-dimensional object, the height is this is a because since you are using height here or length here, this is also known as the linear magnification. There is one more magnification defined, but which you will be studying only in your higher classes. So just go with this. This is also known as linear magnification, and this is the definition of it. It states the magnification is the ratio of the height of the object to the height of the height of the image to the height of the object. Height of the image to the height of the object. There is one more way in which you can derive magnification, and that is magnification M in terms of object distance and image distance. And how do you do that? The magnification is also defined in this manner. M is equal to the ratio of the image distance to the object distance. So there is one more definition for magnification, and that is this. And it is from this equation where you understand whether the size of the object is enlarged, or the image is enlarged, or whether it is diminished, or it is point like, and all that. Okay, so there you go. So basically you have learned three equations. The equation 1 was can I find some space around here? Yeah, three equations that you have learned is the equation for the center of curvature and focus, very important. For the magnification, you have one more two equations, which is this. Actually, both ratios are similar, so I can write it. See, there is no negative sign here. There is no negative sign here. In the case of mirror, there was a negative sign. The magnification m was minus v by u, but in the case of lens, it is just v by u. And there is one more formula, and that was the that was your lens formula, and it goes by, let me just put the box inside. It's 1 by v minus 1 by u is equal to 1 by f, your lens. See, now you may understand why I asked you to put 1 by v first and then 1 by u second, come late, because in the mirror formula I taught you to do this way, because if you do that way, you can compare mirror formula to the lens formula, because in mirror formula it is 1 by v plus 1 by u, but in this case it is 1 by v minus 1 by u. So that is there. So these are the three major equations which you need. So let me not extend beyond this, because it's already you're beyond your, you might have slept like several hours in between learning and listening to this lecture. I know that. Anyways, let me just conclude it here. I will be coming up with next videos later in the next coming week. Thank you guys. Thank you for listening to this lecture at least by 7 hours. Thank you.